Hi, and welcome to this brief lecture giving an overview of the field evaporation principles that are used in atom probe tomography. I'm recording this, and I took inspiration and several slides actually from different lectures given by various other colleagues, and especially from François Vurpillot. Before I start, there are many books that exist on the topic, and that would be probably good if you familiarize yourself with the topic by looking especially at some of the key textbooks in the field, like the Miller, Cerezo, Etherington, and Smith, for example, that goes quite deep into the theory, and more recently the book from François Vurpillot and William Lefebvre and Xavier Sauvage. That goes quite deep into the theory, but also the practical aspects. It was a book designed around a lecture course that they've been doing for quite some years now in Rouen. So where to start with the field evaporation theory? As you can see, there's a paper from Richard Forbes, which is one of the last theoreticians of our field. And the paper is about 25 years old now, but quite little has changed 25 years down the track, because not very many people have worked on theory. One thing that you need to really always bear in mind, and that's a remark that Professor Ed Tarleton made me on Twitter one day. It's like papers are like models. All of them are wrong somehow, but some of them are useful. And so he was quoting a fairly famous mathematician, I think, who said that all models are wrong, but some of them are useful. So what I'm going to explain to you throughout this series, these slides, should be considered as such. It's a way to interpret the data, and it's a model. So it has to be wrong, but it can be useful to understand what you're doing. So let's start with the beginning. What do we see? So let us move back to Erwin Müller and his group at Penn State in the 1950s. They started to evolve their field electron emission microscope, where we apply a negative voltage to a sharp needle and started reversing the bias to generate a very highly positive field. The field emission of electrons is what underpins field emission guns in TEMs, for example. And here we are using more or less the same specimen geometry, a sharp needle cooled down to just a few tens of Kelvin, and you introduce a rare gas, helium, neon, argon, for example, and you observe what happens as the voltage is increased. And what you would see is something like this. Progressively, we start to record a series of images, or an image basically with a specific pattern forming. Why is the specimen geometry so important? Basically, if you want to create a high field, a simple way to do this is to take a curved surface. If you take a sphere, put it in vacuum, and apply a voltage V, the field at the surface of the sphere is V divided by the radius. So if you make a very small radius and apply a high voltage, you get two fields that are extremely high very quickly. So we can't really do this with a sphere easily, but we can consider that the end of a sharp needle is more or less akin to a sphere, or spherical surface, a half sphere if you want. And we can make needles with radius of curvature well below 100 nanometers. And in such a case, the field is the voltage divided by the radius, with a constant here which we call the field reduction factor, or field factor, which some of you might be familiar with. The thing with the field is that it gets distributed according to the surface curvature. So when you're looking at the intersection of a curved surface with a crystalline lattice, there will be a certain distribution of the field that reflects local topography of the surface. And in that case, it actually highlights the position of certain sets of crystallographic planes and where they intersect the curved surface of the specimen. And this pattern is basically similar to what we were observing by field ion microscopy, with this series of concentric rings corresponding to different atomic planes. And here you can see and image individual atoms, because the distance between two atoms becomes sufficiently large that the field variations associated to individual atoms becomes visible. So what happens when we keep increasing the voltage, so the field? We can see that this pattern, ring pattern corresponding to atomic planes is changing, it's evolving, and it's evolving in a quite controlled way, where the atoms on the edges of these terraces are actually field evaporated, removed from the surface of the specimen. And we can see the pattern evolve, and we are basically probing the depth of the sample progressively. And we can also do this by pulsing. So we have a DC voltage, and then suddenly we can apply, for example, in this case, laser pulses tightly focused onto the end of the needle. And under the influence of these laser pulses, we are causing the departure of the atoms from this pure tungsten needle, for example. So how does this work? What is field evaporation? As I have mentioned this briefly, that the field evaporation is the removal of the surface atoms under the influence of this strong field. So the atoms are going to be repelled and transform into ions as they go. And because we have now an ion into an electric field, it's going to be accelerated away, projected away from the surface. This transition from a surface atom into an ion is the term field evaporation process. And to get this process to be efficient, you need electric fields in the range of 10 to the 10 volts per meter, depending on the species that we are considering. And this is why we need these very sharp needles. So what happens if I look at the potential well binding the atom to the surface initially, and now I consider the ionic states of the same atom near the same surface. The difference is in energy is the sublimation energy, and then the sum of the ionization energies for to remove the electrons from this atom. And the surface then would gain, the system would gain the work function, which is the energy that you need to provide to the surface to extract electrons. Here it's gaining electrons. So under no electric field you have these two separate curves. But then the ions, if you start applying a high field, the ionic states would be affected by the presence of the field. And then there's this additional term that comes in that is proportional to the strength of the field. And what that means is that the transition from this atomic state to ionic levels of a higher or lower energy become possible by just hopping there above the energy barrier. And this transition is basically caused by thermal activation, and this is the main model to explain the field evaporation process. It must be pointed that tunneling of the atom through this potential barrier is also in principle possible, but it's much less likely and typically affects only very light atoms. I mentioned briefly this energy barrier that you need to overcome to remove these surface atoms. So again, it's the sublimation energy, the ionization energy, the work function here times the number of electrons that you're removing from the atom to transition into an ion. and this function of the field. And this can be written as a Q0, an energy barrier that you would need to remove the atom without the field, and this function of the field. At 0K, the field that you need to put the barrier to 0 is called the zero barrier evaporation field. So it's typically the highest value that you would need to remove an atom without any thermal activation. The model that Müller proposed, which we know is wrong, like all models, led to estimations of the fields that you would need to remove atoms, for example, from iron or nickel or copper or tungsten, that were actually not too far from values that could be determined experimentally in the range of 33 volts per nanometer, for example, for iron, 35 for nickel, 30 for copper, and about 57 volts per nanometer for tungsten. And there is a criterion saying that the most likely charge state that will be found is the one for which the fields that we are estimating through this model would be the lowest. And this thermal agitation leading to field evaporation was confirmed by looking at Arrhenius type plots. For example, this work by KELLOGG back in the early 80s, trying to estimate as a function of the temperature what was the field that you would need to remove atoms at a given rate of removal of the atoms from the surface. This is the rate there. So you have a frequency at which the atoms are going to try to escape, and this is basically the energy barrier divided by kT. And by assuming a linear relationship between the field and the very close to the evaporation field, we can make this assumption that the barrier will be varying linearly with the field. And if you do this, you end up with an energy barrier without fields of about 2 EVs, which is reasonable, and then a frequency at which the atoms are going to try to escape, which is in the range of 10 to the 12 times per second, which also corresponds to phonon frequencies. So it seems to make some sense at least. So I'm going to briefly touch on one of the more theoretical aspects called post-ionization. So as I've mentioned, the idea is that the atom transitions into an ion by losing one electron. And so far, the models that had been proposed said that the atoms could actually escape with a higher charge state. So not only just 1+, but it could be 2+, 3+, n+. What was proposed in the early 1980s is that the atoms actually are not field evaporating, having lost multiple electrons, but just one, and then as they fly away from the surface, they lose a second electron and then a third electron, and so on and so forth. This theory that was brought forward by David Kingham back in the early 80s in Cambridge is that the same process that was enabling field ion microscopy, field ionization, would be taking these electrons away from the atoms or from the ions as they are departing away from the surface. So we can estimate based on the strength of the field and the ionization energy of the departing ion, whether it is possible for these ions to lose one more electron or two more electrons. And we can then integrate this probability over the entire flight of the ion between the specimen and the detector. So again, you have to make quite a few assumptions for this to work. And there's always a few parameters in that model. I invite you to read Kingham's paper if you can. And he compared the data with some experimental reports of the evolution of the charge states as a function of the temperature and the field strength that were published by Ernst. And it seems to reproduce these trends quite nicely. So here on the log scale, you have the ratio of the different charge states. And here you have the strength of the field as on the x-axis. And what this means is that at low fields, you have mostly rhodium 1+, and as the field increases, you have more and more and more rhodium 2+. And the ratio between the two has to always be 1, so log of 0, right? And what then Kingham proceeded to doing was to calculate what we would expect for a whole range of different elements, with again here the field strength and here the ratio between the different species on a log scale. So at low fields you get mostly 1+ aluminium. As you reach about 20-25 volts per nanometer, then you should get about 50-50 between aluminium 2+ and aluminium 1+. And as you start reaching fields of about 30 volts per nanometer, then some substantial amount of aluminium 3+ will come in. So here it's about 1 in every 1,000 ions will be aluminium 3+. Here it would be 1% aluminium 3+ at like 38 volts per nanometer. So these curves are quite useful and important to bear in mind. Now for some more practical considerations maybe. So how does atom probe work? So we have this sharp needle, we place it in front of the counter electrode. The needle has a short, small radius of curvature. We maintain it at low temperature, we can tune this. Then we apply the high voltage, it generates the high field all around the needle. When the field is sufficiently high, atoms start to be emitted in the form of ions, ionized once or multiple times. And then the field surrounds the needle, and the ions will fly within this electrostatic field, go through the counter electrode, and we collect them onto a position-sensitive detector. Typically, we can operate the machine in two modes. Either we apply DC voltage and high voltage pulses, or we can replace the high voltage pulses by laser pulses, tightly focused onto the apex of the needle, or near the apex of the needle. And why do we do this? Because then we can control the time when the ions form and start their flight. So by knowing when the ion starts and collecting the detector signals, we know when the ion landed. So we can deduce from its time of flight the elemental nature. And then by using some magic, which will be described in another lecture, and this time of flight and a projection law, we can build these beautiful three-dimensional reconstructions that you are familiar with. So in the atom probe, we send a series of pulses, either voltage or laser. And over time, we have this cadency, this repetition rate, which is one of the parameters that you can change during the analysis. And every time you send a pulse, you start a detection window during which all of the signals that are collected onto the detector will be considered as an ion that was detected. So sometimes you send a pulse, you detect nothing, a blank event. Sometimes you detect one event, sometimes you detect multiple events, more than one ion detected at once. And then you keep going and you keep going. By integrating all of these events, you actually get to a stage where you can count how many ions have been detected per unit of time or per pulse on average. And this is one of the parameters that you can also tweak during your experiment. As you know, one of the results from atom probe is a mass spectrum. So as I said, we collect the times of flight and we convert those into mass to charge ratios. And here we have counted a number of ions of a specific mass to charge. For example, if I zoom here, I can see that I have collected a number of ions corresponding to the different isotopes of chromium, of vanadium, of the isobar between iron and chromium, and then of manganese. Yes, it is a piece of steel that was analyzed. So if I go back to some more theoretical considerations that actually have a practical influence, I have told you that the field evaporation was a thermally assisted process. and the barrier that you need to overcome to remove the atoms is actually dependent on the field. So if I consider a certain rate at which the ions are being detected, then at a low temperature I need a high field, and at a higher temperature I will need a lower field. So what I want to do is set a base temperature for my experiment, and then a certain DC field, because afterwards I will have to pulse. And what do I have to think about? I have to select conditions where at the DC field and at the base temperature, the field evaporation rate is basically zero, it's null. Otherwise I will start to have ions flying all the time, and that's not what I want. I want to be able to time the departure of the ions. So either then I can use high voltage pulses, and in that way I am pulsing the field. So I go from this position where I'm not causing any evaporation, and I'm increasing the fields until I cross this line where I'm going to start field evaporating at a fairly high rate, a detectable rate. The alternative is to actually increase the temperature with laser pulsing. So the laser pulse will be absorbed. Some of the light, by absorbing the light, the specimen temperature will increase and then will cool down. So basically we are increasing the temperature and then decreasing the temperature in the same way that we were increasing the field and decreasing the field. So we don't field evaporate at just one rate. We can change the rate at which we do the evaporation. And what we want is always to be in conditions where it forms a network of curves like this. And what we want is always to go from conditions where we are not field evaporating to conditions where we're field evaporating during the pulse, laser, or voltage. And if we do this, we end up with a mass spectrum that makes sense. We control the time of flight well, and we have a low level of background that's mostly related to the DC, to the dark current of the detector, and also some of the ionization of the residual gas that happens at the DC field, so we cannot time it. There are experimental proofs that effectively we can track the field through the charge state, as I've mentioned before. And if we start increasing the temperature, we can see that the charge state on average drops. So the field actually drops on average. This also applies if we track the laser pulse energy, which means that as we increase the laser pulse energy, we actually increase the temperature at which the field evaporation takes place. And this results in a change in the charge state and the field. Now, as I've mentioned, the probability to field evaporate is more or less this Boltzmann law, Arrhenius, depending on which way you want to see this. So if we look over time, if we send a pulse, which is a few nanoseconds typically for a high voltage pulse, the probability of field evaporation will be happening over a fairly sharp, short amount of time. If the pulse was much broader, then the probability for field evaporation would also be much broader. And that's typically what happens with laser pulses. So you will start to warm up quite quickly, but then the decay of the temperature can take a lot longer, and this will depend on the specimen geometry. And experimentally, we can see this quite clearly. The peaks in high voltage pulsing are always the same, more or less. But sometimes when we change the laser pulsing conditions by going to a very high laser power, for example, so we're heating up the specimen quite to a high temperature, it will take longer for the specimen to cool down afterwards. So you have these long tails, for example, that are related to the probability of field evaporation over a longer period of time. So going back to this graph, which is very important to always bear in mind, if I consider this position here, I am effectively not causing field evaporation during a high voltage pulse or a laser pulse. But what happens if I increase the base temperature? I might actually be in conditions now where I am constantly field evaporating at a substantial level, although I'm just at the DC voltage. Same thing, if I start to increase the DC voltage at the base temperature that is lower, I might start to field evaporate at a substantial rate. This will cause a lot of background, because we're going to now have a lot of ions generated at the DC voltage, so not associated to a pulse. If it's not associated to a pulse, I cannot measure its time of flight, and this will appear in the form of a background in that shape. And if the background is too high, you're going to start hiding peaks underneath, and you're also losing some of ions from the analysis, so it's really not very good. And I can tell you that often when I go and check out the analyses that are running, I see the level of background being quite high, and this is not good. So you should always pay attention to this. This is a sign that the analysis conditions are really not ideal, and you are field evaporating at the DC voltage, either because of too high a base temperature or too high a field. So you are basically asking too much from the specimen in terms of detection rate. So how can we deal with this? We can, for example, change the base temperature or change the field, so the detection rate that you're requesting. And for example, here, by lowering the field, we're going to go back down to good conditions where the background will just go back down into at a reasonable level. One of the added complexities is when we have a sample containing more than one element, is that each element will have its own network of curves and with different slopes, for example. And so we always need to be paying attention to being in conditions here where we are not field evaporating either one or the other element at the DC voltage. And it's typically quite clear that by looking at the composition that we are losing one element or another. And typically it means that the level of background that we're seeing is going to be made preferentially in, for example, of B or A, and that will affect our capacity to measure the composition accurately. It is a very well-known problem. For example, in these old papers from the 80s, they were already reporting this, where they were missing silicon or iron in the analysis of an iron-silicon alloy. And for example, in that case, from later, from the early 2000s, or mid-2000s actually, from David Seidman's group, where they were looking at the aluminium, chromium and nickel composition as a function of the laser pulse energy in a superalloy. So let me conclude this first lecture, and with some aspects to keep in mind. Atom probe relies on field evaporation. Field evaporation is primarily a thermally assisted process whereby the surface atoms get detached in the form of singly charged ions because of the electrostatic field pushing them away. These ions can then undergo post-ionization, whereby these singly charged ions get further ionized by the removal of electrons that tunnel back into the surface because of the strength of the field. The control over the field evaporation comes from the use of pulses. So either we use high voltage pulses to increase the field for a short period of time, or laser pulses that increase the temperature for a short amount of time. And that allows us to time the departure of the ion and measure their time of flight and hence their elemental nature using time of flight mass spectrometry. The analysis conditions must be adjusted in order to ensure that ions from all the different elements from your material are coming because of the pulse and not at the DC field. Otherwise, they are lost from the analysis. Thank you for your attention.